Have you ever looked in the mirror and, really thought about what's going on? I mean, beyond just checking your hair. How does a simple, flat piece of glass manage to create a perfect, reversed copy of you? Well, let's dive in. It turns out the physics behind your reflection is actually surprisingly simple. And once you get it, you understand everything from a wild funhouse mirror to the most powerful telescopes in the entire universe. So here's our roadmap for today. First, we're going to tackle what light is, at least for our purposes. Then we'll get into the super simple rules of reflection. After that, we're going to start bending those rules with some fun house mirrors. And finally, we'll learn how to actually draw with light so you can predict what any reflection is going to look like. All right, first up, light's two faces. See, to really understand how mirrors do their thing, we first have to decide how we're going to look at light. Because believe it or not, physicists see it in two totally different ways. When you get right down to it, the study of light, or optics, splits into two big categories. You've got wave optics, which is super complex and deals with all sorts of wavy behavior. But for what we're doing today, understanding mirrors, we can use a much simpler, more direct model, ray optics. This approach just treats light as a bunch of perfectly straight lines, or rays. It's the most straightforward path to figuring out how your reflection really works. Okay, so now that we're on the same page, light travels in straight rays, we can uncover the rules they follow. And honestly, this is the best part. It all boils down to one fundamental idea and two super simple, unbreakable laws that work for every mirror, no exceptions. So it all kicks off with a principle that has a pretty fancy name, rectilinear propagation. But don't let the name fool you. All it means is something you already know deep down. Light travels in straight lines. Seriously, just think of a laser pointer. That perfect, straight beam, that's this principle in action. Every single ray of light from the sun, a lamp, whatever, does the exact same thing. So just picture it. You have a light source, maybe a tiny light bulb. Rays of light are just shooting out from it in every possible direction. But, and this is the key, each one of those individual rays travels in a perfect straight line until it slams into something. This one simple fact is the foundation for absolutely everything else we're about to cover. And based on that straight line travel, we get these two ridiculously simple laws. Law number one, the angle a light ray hits a surface at is the exact same angle it bounces off at. It's just like playing pool. The angle the ball hits the bumper is the angle it comes off. Bam, equal. And law number two is even simpler. The incoming ray, the outgoing ray, and that imaginary line that's perfectly perpendicular to the surface, they all lie on the same flat plane. That's it. Simple, clean, and always true. So what's the result of those two simple laws? Well, they perfectly explain your bathroom mirror. Your reflection always looks like it's the same distance behind the mirror as you are in front of it. The image is always upright, erect, and it's the exact same size as you. The only weird thing is that it's laterally inverted. If you raise your right hand, your reflection raises its left, every single time. Okay, so that's a flat mirror. Pretty straightforward. But what happens when we start to bend that surface? Well, now we get to the really fun stuff, spherical mirrors, aka funhouse mirrors. So if we curve the mirror inward, kind of like the inside of a spoon, we've made a concave mirror. And watch what it does to light. It takes all those parallel rays and focuses them, or converges them, all down to a single point. That's why it's called a converging mirror. It's a collector. It gathers up light and energy and concentrates it. Now, what if we flip that spoon over and curve the mirror outward? Well, now we have a convex mirror, and it does the exact opposite. It takes those same parallel rays and just spreads them out, scattering them. They diverge. This scattering effect is exactly why the passenger side mirror on your car says objects in mirror are closer than they appear. It's a convex mirror giving you a wider view. So we've got mirrors that gather light and mirrors that scatter light. But how can we predict exactly what kind of image they're going to create without just looking? Well, that's where our final section comes in. We're going to learn how to draw with light. Okay, these three rules right here, they are the ultimate cheat codes for figuring out any reflection in a curved mirror. Rule 1, any ray that comes in parallel to the center line bounces off through the focal point. Easy. Rule 2, any ray that goes through the focal point first bounces off perfectly parallel. See, it's just the reverse of Rule 1. And Rule 3, the easiest one, a ray that passes through the mirror's center of curvature just bounces straight back along the same path. You only need to draw two of these three to pinpoint exactly where an image will show up. All right, let's actually try it. Here, we've placed an object pretty far from a concave mirror. So we draw one ray parallel, and it reflects through the focus. We draw a second ray through the focus, and it reflects parallel. And look, see right where they cross? That's our image. Notice, it's smaller, it's upside down, and it's what physicists call a real image. That means if you actually put a little screen right there, the image would project onto it, like a tiny movie. The light rays are physically meeting at that spot. But watch what happens if we move the object really close to the mirror, inside that focal point. Now, when we trace the rays, they spread out. They never cross in front of the mirror. But if we trace those reflected rays backwards, behind the mirror, they meet up. This is exactly how a magnifying makeup mirror works. It creates a virtual image when you can't project on a screen that's upright and way bigger than the real thing. So what's the big takeaway from all this? It's not really the mirror that's in charge. It's the position of the object relative to the mirror. That exact same concave mirror can make an image that's tiny and upside down, or one that's massive and right side up. The only thing that has to change is where you place the object. So we figured out how a makeup mirror works, right? You put your face close to a concave mirror to get a big, magnified virtual image. That leaves us with one final, kind of mind-blowing question. What happens if you do the opposite? What if the object isn't super close, but is practically infinitely far away, like a star? How could you use these exact same physics to take that faint, ancient starlight and focus it down into an image you can actually see? Well, that's the secret behind every major reflecting telescope on Earth, all using these simple rules to see to the very edge of the universe.